Good morning, good afternoon, depending on where you are in the world. My name is Steve Downey. I'm a software engineer at Bloomberg. This talk's going to be about the various algebraic and categorical structures that we use to talk about C++. A very long time ago, I had a math degree. Well, I guess technically I still have a math degree. Most of the math that I did, though, was on the analytics side, doing calculus and differentials and numerical. And this is was not my field. I've learned it later just to be able to keep up with the programming theory literature. So why don't we get started? So sums, products, exponents, monoids, functors, oh my. It's an algebraic bestiary. Oh. So why should I care about this? This is a lot of abstract nonsense in practice. The important thing is really to understand that all of this jargon that gets thrown around is really trying to get at terms of art. We're trying to be clear in how we convey things to each other, how to convey meaning concisely without having to constantly redescribe everything from the ground up, which can be tedious. It also turns out that when we follow the meaning behind these terms that I'll be introducing, we can come up with better code that composes better, that operates the way people expect. There are fewer surprises, and surprises are always something we try to avoid. We're going to be talking about types and structures. And generally, this is going to be broken down into three parts. We have algebraic types, where the algebra is composition of types. Algebraic structures, which are patterns of operations on those types. And then higher order structures, where we have patterns of composition of the operations. So, part one, basic algebraic types. And algebraic types is about manipulation of types with the rules of basic algebra. We add, multiply, and exponentiate types with each other. Getting into what that means. But essentially, we're going to be able to use the basic rules of algebra that a lot of us learned in high school, that in order to show how types work together, when types model the same thing or can be used to model the same thing. Now, the underlying algebra is roughly based on counting how many objects are in a type. So it's like if you have a bool, there's true and false. So there are two things in that type. One of the basic things in C and C++ are product types. These are structs, where structs have names of the elements, and we refer to those things by names. But we also in C++ have pairs and tuples. And the product part comes in because when you have a pair of int and bool, that type gives you 2 for the bool times however many ints there are, depending on the size of your int. And that's how many different objects can be in your type at most. Together with product types, we have, sum types. The basic sum type in C and C++ is the union. Unfortunately, union's very limited into what we can put in the union. There have been various proposals over the years to have some sort of better sum type in the language. But we do have in the library variants, which give us most of the power of general sum types. We will set aside the problems of references for now. Some other sum types that are either in now or coming up are things like optional or expected. And the reason they're referred to as sum types is when you're counting how many things are in there. If you have something that is either a bool or an int, then you've got the two bools plus however many ints there are to describe how many things are in the type. So this gives us addition. We also have our void and monostate. So void is the empty type. It's our 0. And monostate is our singular type and is 1. The empty product, a tuple of no types, has exactly 1 member and can be instantiated. The empty variant, which is an or of nothing, has no members or objects in it. C++'s void is not void in this sense. There are expressions of type void. And you can read some of the various papers on regular void because it would be nice if we could treat the lowercase v void more like other types. It's been argued that stood monostate, which is a type used in variants, ought to be really the stood tuple of nothing, except stood tuple is really expensive to compile, and that wouldn't be nice for everyone to have tuple exposed to them when they just need a type that has exactly 1 element in it. Now, we have addition, we have product. What we also can have are exponential types. And it turns out that we can talk about functions from type A to type B as being B to the A algebraically. And again, this comes down to counting things. So if we have, for example, a unary function, let me zoom a little bit here. You can see everything a little bit better. No, well, yeah, it goes off the edge of the screen on this display. Sorry, but we can have examples of functions where if we have a function from A to bool, one of the simplest kinds of functions we could have, and we have A has 3 elements, A0, A1, and A2, and we can define in a table 8 distinct functions that are possible. Any other function that we tried to define from A to bool would be equivalent to one of these, even if it was mechanically producing values by a different mechanism. But we could say, starting from the first function f0, which returns true for everything, running to the last function, which returns false for everything, and we just have a basic table here, which is essentially running, if we replace true and false with 1 and 0, This would be counting to 8 in binary, and that's exactly why we can talk about functions as being exponentials, because the tables get large fast because exponentials get large fast, but this gives us some idea of how this is, can be thought of. An important property to discuss is, when are things the same type? If I have two different types that both have two objects in them, how do we want to say that those are equivalent? Because there's some natural intuition that there's an equivalency here. And what we want to talk about is isomorphism, that there's a same shape. And by that same shape we mean that there's a mapping in both directions from one type to the other. Okay, actually, let me switch back because that was a good question. The table looks like the possible inputs to such function. Let's switch back quickly. This is a mapping of outputs of the function. So the entries in the table are f of a0, a1, or a2. So that it's like basically F0 returns true for A0, returns true for A1, returns true for A2. Similarly, taking in F3 returns true for A0, false for A1, false for A2. And we're just looking at the functions from the outside. What do we observe them to do, not how do they go about deciding what their output are. So two functions are equivalent if they give the same result for the same inputs. And this fits together with what we mean by the same type, that there's an isomorphism. We can define a mapping in both directions from one to the other that is complete and say onto, so that we can say two types are the same if we have a mapping from one for each element to a distinct element in the other, and a mapping in the reverse direction from each of those elements back to the same element on the in the first type. In terms of algebra, we can define normal form, and we can prove, although I won't go into the proof, that types with the same normal form are isomorphic. And normal form is conventionally sum of products. So we can look at some type formulas. So optional A has the formula 1 plus A. So optional adds an empty state to A. And pair of AB is A times B. The objects of pair AB have all the Cartesian cross product of the elements in A and the elements of B. Monostate, which has just one element, has the formula 1. Bool, which has just true and false, has formula 2. True, false, file not found, and enum, that's formula of 3. Struct A, named A, semicolon B, named B, has the same type as pair. We've added names to the type, but all the operations on it can be mapped back to pair. Is there a meaningful type whose formula is 0? And that's, the empty type, canonically known as void with a capital V. You can have a type that's the empty set. And if you try and put that empty type in a struct, you can't have any elements that struct, because then you can't have any elements that would fill that out. So it works as the product. You can also, but you could put it into a union type, because you could then just never be able to actually have a object that has the void type in it. So it would be 0 plus A for a pair of A and void. Unions have a plus type. Variant ABC is A plus B plus C. We can also manipulate these formulas. So a variant of A, or a pair, is A plus A, which is 2 times A. And a pair of bool to A also has type 2 times A, or 2A. Now, basically, a tagged pair is equivalent to a variant. So that bool tells us which A we should be talking about. So we can make that equivalent to and answer the question, was this the first A or the second A in that union? You can write that mapping and use those equivalently with those mappings in other algorithms. Now, if we look at tuple, if we had a tuple of A, that's A times A times A, or A to the third, which is the same formula as a function of 3 to A. So basically, a function that takes an index and returns an A is equivalent to a 3 tuple, or equivalent to an array of 3 elements. So we can go back and forth with different representations of our types without losing meaning for them. Another interesting thing to look at is recursive types. So if we have a list here, L, which is either null or a value followed by a list, which means that we have the formula 1, that monostate nil, or an A followed by a list. And we can expand in L, so replacing the L on the right side with the formula 1 plus AL multiplying through, and we can see that that these are a list is nil, or an A, or 2 A's followed by a list. The formulas are not about functions. The formulas are showing equivalency in types. So that there's basically that if the two formulas are equivalent, then the types are equivalent. So we can keep expanding this recursive type, and you can see that by continuing the expansion, it's like an L is a nil, or an A, or 2 A's, or 3 A's, or 4 A's followed by a list. And as a sort of quick aside, it's like we can actually do some calculus with these formulas. It's been shown that the first derivative of an algebraic type by its formula is the type of its one whole context, which is a zipper type, which basically opens up, for example, a list or a tree, allowing you to do operations focused on some element, and then move to other elements in reasonable time. And the derivative tells you what the type of that zipper is. Okay. checking time. Yeah, we're on track. So part 2, we're going to talk about algebraic structures. And algebraic structures are types with operations on those types. These kinds of structures not only guide how the operations should behave, but inform what constructors should be provided for a type. So the simplest, interesting structure to talk about are known as group-like, and this is one type and a binary operation, A to A, yielding an A. And these are also known as group-like. There are sort of 3 interesting properties to consider about the operation, whether the operation is associative. That is, can you put, if you have A plus B plus C, can you do those operations in either order? So this is important to, for example, if you doing a fold and want to know if your left and right fold are going to be equivalent. If the operations is associative, they are. Another question you can ask about the operation, is there an identity with respect to that operation? So that such that if our operation is plus, A plus I equals A. For addition, the identity is 0. For multiplication, the identity is 1. For other operations, there are other identities. Go into that in a little more detail in a couple of slides. We also can ask, is there an inverse operation? That is, for all the elements of A, there exists some element A prime such that A op A prime gives us the identity. And knowing if something is invertible means we can go backwards in our computations. And sometimes this is useful for certain algorithms. Another trait we consider sometimes is commutivity. That is, if A plus B is equivalent to B plus A. This is usually known as abelian, after the mathematician Abel, who produced a bunch of this theory. So abelian groups have commutivity. This is very important for things like parallel algorithms, because if you don't have to preserve order, you have a lot more freedom in how you structure the computations. So given those 3 properties, we can construct a taxonomy and give all the options names. But first, a quick disclaimer. All of this theory has been developed over more than 100 years. Some of the terminology varies slightly in various fields and subfields. Papers, entire books, they'll start with definitions that hold for the scope of that writing. So don't panic. Generally, it's always fair to ask, for example, it's like, when you say group, do you mean this set, or do you all? Are you assuming that it's commutative? And someone will say, well, of course, but that's okay. Names that are roughly standardized. It's like we have magma, which is the simplest structure. All it says is there is an operation that maps from a pair of A's to an A. If you saw Christobella's talk on discovering the concepts for an algorithm, stating this in C++ for an algorithm requires a fair degree of complexity, because you want to be able to cover situations where, say, ints convert to doubles or doubles convert to ints. And you want to be able to say that you can swap those 2 types, because otherwise people are unhappy with your algorithm. So I won't be going into how to conceptify these here. Semigroup adds the property that the operation's associative. Monoid adds that there's an identity. Group says that it's associative, has identity, has inverse. If we sort of go on the other side of the ladder, where we don't have associativity, the unidal magma, which means there's a magma with identity, quasi-group, where there exists inverses, loops, where there's an identity and an inverse, but we're still not associative. And there's also inverse semigroup, which has a semigroup with an inverse, but doesn't have identity. The simplest one that has the most direct impact on code is monoid. It shows up because if we have a monoid, we can work by parts in any order, and we have an initial element for when we're working with these. These show up when we're trying to apply folds, tree operations, scans, etc. In particular, it means you can, instead of having to provide the initial element for your fold, you can assume the identity element. And if you're missing one side of your binary tree, you can assume the identity element. Trees are particularly interesting when operating with monoids. You can construct trees, for example, that index a data set, possibly in multiple ways, and monoid preserves just enough information to allow you to search through the tree. That you can compose by monoid operations and know, for example, how many elements are further down the tree, or which side has the max element, or which, when you're doing a search. Now, we don't have a function, a standardized function, or at least yet, that returns identity. This is often called M0 for monoid 0. We do have the default constructor. So if you're writing a type that is trying to express that it's a monoid, giving the default constructor the identity element can be very useful. So some examples of monoidal operations. It's a plus, where your identity is 0, times, your identity is 1. Concatenation, where identity is the empty list or the empty vector. So you can concatenate collections together, and concatenating the empty collection gives you the same collection as you started with. Min and max are monoidal, where identity is in min or in max, or standard numeric limits, max or min. For a more general type, you may need to add an additional element to your type to represent the less than anything or greater than anything element. But that can be very useful when you're trying to search or sort by these kinds of things. If you choose to write the operation as a free operator, natural spelling is going to be operator plus. And if you do that, write it as a hidden friend, which means defining it as a friend, not just declaring it, but putting the definition in the body in your class. This will make it available if there is a T involved in your in name lookup, but it won't make it available for other types. which means that you won't have the compiler spitting out several hundred possible pluses which don't match. I'm sure everyone has seen the operator left shift for O stream, and all the O streams that are visible get spit out by the compiler because you didn't write yours correctly. Now, operator plus, often we'll see complaints that, for example, string concatenation isn't really a plus because it's not commutative, and arguments that in literature we would disambiguate that somehow by perhaps writing circle plus as an operation to say this isn't just plus. C++ does not have general operators. You can't just make a new symbol and operator. Also, it wasn't until fairly recently that papers would choose to use notation like circle plus, or it's like other interesting math symbols, because until we had electronic typesetting and LaTeX, it was hard to do. You had to go find a typewriter that had that symbol for you, or handwrite it in, which was expensive in terms of publishing. The prevalence of LaTeX has really changed how papers are published. Now, the other structure that shows up quite often are groups, particular abelian groups. Groups add an inverse operation to the monoid, meaning that you may be able to undo an operation. And commutivity means that you can compose things in either order. It's very useful in terms of concurrency. And commutivity together with associativity means that you can, if you're doing async composition, you can do your composition as soon as the answer is ready and not have to wait for everything to show up. Now, we can signal this with concepts, particularly because by at least convention, concepts have semantic requirements other than syntax, but we don't have a way of saying in C++ directly that this operation is commutative, or even really that this operation is associative. But by specifying the concept, we document that our algorithm is making assumptions about how the things that it is handed work. Now, if we have one type and two operations, we have something called a ringoid. Ringoids generally look number-ish. Things like integers, floating points, big nums, complex numbers, vectors, matrices, because basically you'll have, for a ring-like thing, two operations, plus and times, where times distributes over plus. This is part of the definition. Some important ringoids, you'll have a semi-ring. That means both operations are semi-groups. So we know certain things about how those individual operations behave. For ring, the additive monoid is an abelian group. The commutative ring, inverse for multiplication, it gives us a field. So we have division, where division is closed. So the real numbers are a field where integers aren't. So we could talk about the semi-ring, where it's like our ring with the operator plus is a commutative semi-group. behaves as we expect. Times with times is also a semigroup and distributes over multiplication. Left and right distributes over addition. If you're writing a type and you're expressing operator plus and operator times, you want them to work this way, or people will be very upset with you, or make they will make implicit assumptions about how these operations work. If they don't, you'll have bugs. This is often why people are so hesitant about operator overloading in C++, because you can overload the operators to do things that are really unrelated to people's expectations. So ring, we add a few more rules about how things operate. That we have inverses, so there for all a, there exists a negative a that's in an element such that negative a plus a equals 0, which is the same as a plus negative a. The negation works the way you expect, essentially. That there's an identity element for the multiplication operation, and the left and right still distributes over addition. Field is a ring with division. So for a field f with plus and x, there for any f not equal, any element in f not equal to 0, that there's a times the inverse of a, which equals 1, which is also the same as the inverse of a times a. And again, it's like if you're providing these operations, you want to make sure that they work this way. If they don't, you probably want to give your operations some other name. Now, so let's get into part 3. We're going to be talking about higher order structures and composing operations. And these are coming largely out of category theory, which grew out of abstract algebra. Category theory studies morphisms or arrows, function-ish things, largely ignoring the objects in the type. It's concerns with how operations compose and what structures of composition allow us to reason about those compositions. It's provided many useful results and a lot of really terrible names. Categorical structures are generic types over some underlying type. So something like a class T over A. And in terms of category theory, we assume that all the instantiations, that no matter what A we provide to T, to the template T, we get the same behavior out of it. That's not strictly true for C++, which is very useful and sometimes dangerous. For the classic case, vector bool isn't really quite a container and has a lot of strange behavior because it's specialized to behave differently. Or we might choose not to provide a specialization at all for some types. Because there's some variation in notation. I just want to say, when I'm talking about function composition, if we're composing f over g of x, I'm going to be writing that as f circ g or circ of f of g. That has a type, the circ operator, beta to gamma and alpha to beta compose into an alpha to gamma function. So a function that goes from B to G, and a function that goes from A to B compose into a function that goes from A to G. Just how you would expect. You can write this in C++. We'd have without going into a lot of ceremony about defining restrictions on the parameters. But if we pass it a function f and g, this returns a lambda that takes generic x and returns f of g of x. Being able to return lambdas from functions gives us a lot of power in C++. Now, the simplest categorical higher order thing we're going to be talking about, I'm going to talk about is Functor. This is one of the unfortunate names. They actually got here first, but in C++, Functor was often used to talk about function objects, types with a call operator on them, which leads to quite a bit of confusion. Functor allows functions to be mapped into the type in such a way that it composes sensibly. Containers are natural functors and is the easiest intuition about what a functor is. That there is at least one value somewhere inside the functor that you can apply functions to. Now, not all functors are containers, but the intuition generally holds. The defining interface for a functor is fmap or transform in C++, where we can take a function from A to B and apply it to a t over A and get out a t over B. So we're applying our function from A to B. So if we have a vector of ints, I can fmap or transform that into a vector of doubles. There are a few laws that we can't demonstrate in terms of code, even in terms of mathematical proof. That it's like if you're claiming if something is a functor, you have to show that your fmap behaves as expected. Essentially, that if you apply an identity function to your functor, you get the same thing back. And if you apply a composed function, it's the same as composing transform on either side. Essentially, a composition distributes over fmap or transform. This looks complicated written down, but on the other hand, it turns out to be intuitive, and people actually rely on this all the time. So C++, we have stud transform, classic algorithm where I've elided, it's like all of the concepts and requires clauses that go into this. But essentially, we have transform that'll take a two input iterators and put the output into an output iterator, where we have a unary operation, which is just taking our A and turning it into a B. Ranges transform, which does the same, only taking a range, and the output. We also have recently added transform to optional. So you can map your function into the optional, and this takes care of the empty case in the optional all by itself. So your function doesn't have to deal with empty optionals. The transform does that for you, which is one of the reasons we like these sort of higher order functions. These functions can deal with the context in ways that make sense, so that your functions can deal with their business and the golden path. Now we're going to get into one of the scary categorical systems. Oops, hit that too long, sorry. Okay. Yeah, sorry. So monad allows functions returning the type of a monad to be bound into an instance, or two functions that return monads over different types to be chained together. So it's still about composition, and the signatures are actually less scary than the words. Monadic types can also be flattened, so if we have an optional int, we can just flatten that into an optional int. If we have a vector of int, we can just concatenate all the vectors together into a single vector of int. And basically, an intuition for this is a context for computation, where your computations are the base functions that you're putting into the monad, or mapping in, or combining in various ways. The interface is bind, or and then, which is what we've chosen for optional. We take a monad over A and a function A returning a monad over B, and then we'll then give you that monad over B. So that means we can bind our function, for example, with optional. I can take a optional int and a function returning int to optional double, and return an optional double out of this function. The interesting thing here is that your function, because it's returning this monad, has some information about what has happened before. So for you might only return your double inside the monad if the integer was even, and otherwise return an empty optional. And so the result comes out will be either an empty optional or a double that was the same as the integer, for example. So we can change the context that we're operating in, and this is the heart of the additional power that monad has over functor. The fish, or Cleasley arrow function, is basically monadic function composition. We can compose a to monad B together with a B to monad C into a function A to monad C. Very often, the one or the other of these, or possibly the third one, the flattening, joining, or concat operation, is easier to implement or think about. However, it also turns out that any one of these combined with one of these other operations, where make, pure, or return is another name for this function, but basically being able to lift a into your monad A. So this would be turning the integer 1 into a vector that of integer with a 1 in it. This isn't always the constructor, for exactly the reason that the vector constructor with int gives you a vector of zeros of int size. We want to be able to distinguish that I'm putting a thing into the monad. That thing might be a value, that might be a function, which functions are values. And all monads are functors. So we also have the fmap or transform, which gives us an AB into and a monad over A, returning a monad over B. As I mentioned, won't show the proof, but any of the first three and one of the second and two, you can use to define the other three. Basically, like the join and bind work together in a predictable way. You define one in terms of the other. This is not necessarily the best definition, might not be the most efficient, but it'd be correct. And if you're saying your type supports a monadic interface, you should make sure that it actually does those things. There are a few laws, rules that your type needs to follow. Basically, here, if H is a monadic a function that returns a monad, it's like binding a lifted into the monad with the monadic function is equivalent to just applying the function to the value. That on the right side, if we have M, which is just the type constructor for the monad, and pure, if we bind those together, we get just the type constructor. So we can make your monad out of that. There's an associativity rule, which is a little hard to read, but if we bind three functions together, it's like binding the type constructor together with binding a lambda that lifts G and H together. As I mentioned, the interesting power of the monad is that they can change the context. So if you bind in a or and then a function that returns an optional or a vector, you can change the kind of vector. You could have a different number of elements in the vector. You can make your optional be empty, whereas you can't do that with fmap. Fmap has no access to the context that it's running in, whereas and then does. So the monad returning function passed into bind can change everything. Looking at optional quickly, we have and then and transform, which are the core operations that we're talking about. And then is also known as bind, transform, also known as fmap. And there are additional constraints on these functions about what they return. And then is used for functions returning optionals. If you applied transform with a function returning optional, you would get an optional. And this is essentially how flatten or join comes into play, because the rule is that if you join that fmap, it's the same as if you had just applied and then. A small example of implementing some of these functions. This is from a different library I've been working on, implementing lazy evaluation using coroutines. We have a lazy type where there's an underlying get that does the evaluation, pulls it out. we can construct a lazy that co-returns whereas that will suspend at that point, and when it unsuspends, it just invokes its arguments. Can implement transform on this, given a lazy value in a function. It's just we return f on L and f evaluating the lazy. Join, another name for flatten or concat. In this case, we can implement that just by evaluating the lazy value, stripping off the outer lazy from it. For the bind operation, we're going to take a lazy and have a function where that function is constrained to return some sort of lazy, and we just evaluate that. F on evaluate the lazy. What I'm getting at here is that the implementations of these functions are generally small and natural looking in terms of whatever type you're operating on. There's also a large number of monads, but you are probably not going to find a new one. You may need to still implement it for your own purposes, but there are fewer monads than there are, say, functors, and it's like fewer functors than there are, say, groups, because each of the constraints in these systems means certain things just can't be. So with that, are there any questions or comments?